reversals. There's always a big fluctuation when you get a reversal, but by no means every big fluctuation leads to reversal. So that's a comforting thought, because it means that in all probability, all our problems over South Africa are much more likely to be solved by coming back up again than they are by going through a full reversal. So
how long back was the last reversal, you said?
The last proper reversal was 700,000 years ago. 700, and they occur roughly on average 300,000 years. So we've had a long innings of single polarity, actually, comparatively long innings. Mind you, as I said, in the Cretaceous there was a 60 million, it's called a superchron. It seems to be the same polarity for 60 million years, which is sort of fairly astonishing, really. And so that's about it. So I want to wrap it up. I'll just leave you with these sort of what I consider some of the major problems in planetary dynamo theory. And you can see almost every planet has got a problem associated with it. But that's partly due, I think, to the fact that, as I said, this dynamo action planets is relatively critical, basically due to this fact that the magnetic Reynolds number is not huge as it is in planet is in stars and galaxies and so on, so that small variations from one planet to another can mean that one has a magnetic field and the other one doesn't. Okay, thanks. That's
thank you, Chris.
That's the stop. Thank you.
Any questions, please? In ask, yes.
So, are there reversals for the other planets, and do we know anything?
We don't really know that. The picture on Mars is, I mean, if you remember the picture I showed you on Mars, it has lots of sort of red and green stripes there, which sort of suggests that parts of it formed when it was one polarity and other parts formed with the other polarity. But if you actually think a bit harder than this on that, it becomes much less clear, because remnant magnetism is a slightly weird thing. If you have it's the differences in magnetism which are really crucial. So if the crust was slightly bended like that, then you could end up with a picture with stripes one way and the other way, even if it was cooled during even if that rock was actually laid down and went through the Curie point, actually when it was in one field. So you can't really be sure whether Mars field reverses or not. The last meeting on planetary dynamos, this came up, and there was quite a big argument, because some people took on face value the fact that it's reversed and not reversed, that indicated that Mars field had reversed. But the majority view at the end, when we'd actually sorted it out, was that it could have done, but the evidence isn't there.
How do we know that the Earth dynamo is working, is not just decaying? There is evidence that...
there's paleomagnetism here is a measurement of the magnetic field laid down in rocks. And when you go and dig up the rock and put it in your laboratory, you can find out how much remnant magnetism there is there. And it looks very much as though that what you get there relates to the magnetic field actually at that time. If you then dig up another rock somewhere further away, you find that they correlate for the same period. So that all the rocks that date to a certain time when you were at one particular polarity actually relate to that polarity.
So I'm just saying right now, it could probably work, for sure it worked in the past, but do we have evidence that dynamo is working right now?
Oh, well, I guess the answer to that is no, because that picture I showed you showed that in fact, not only is it decaying, it's actually decaying faster than free decay. I think it will be, if it's been working for 3.5 billion years, it's unlikely to have suddenly taken into its head to switch off. I mean, we know there's an internal magnetic field. I mean, that's certain. I mean, you can, by measuring the Gauss coefficients and their variation with height, we know that there's an internal field, so there's no question the source of the field is the inside of the Earth, not the outside of the Earth.
But you could have like Mars, right? That Mars lost
yeah, but the Earth's field is far too strong for it to be currently due to remnant magnetism alone. Remnant magnetism only leaves behind a relatively weak field. It's almost a factor, I think, a factor of 1,000 down on the source field. So that the Martian field is much weaker than the Earth's current field. You know? But it's still surprisingly strong for a remnant field, but it's still much lower than an actual, genuinely. So that's why.
Could you elaborate a little bit on Cowling's theorem? Is it there in a simple picture why you can sustain an axisymmetric field?
Well, yeah, I think Karl Heinz mentioned that, but basically, if you want a dynamo-driven field cannot be purely axisymmetric because there are two ways of thinking of this. One, Cowling's original argument was essentially there'll always be a place where the magnetic diffusion overcomes any generation. Yeah, that's one argument. And then there's the Brzezinski argument, which essentially expands everything into toroidal and poloidal. Yeah, and basically you've only got poloidal and so it decays away. Basically, you can't have it like that. So it's yeah. So I mean, a dynamo process has got to be due to the interplay of toroidal and poloidal magnetic fields.
So when Brzezinski had his models back in the 60s, what was then the ratio of?
Oh, well, Brzezinski, yeah, that's something that sort of changed. I mean, Brzezinski's idea there, his paper was called the almost axisymmetric dynamo, and he had this idea that it was nearly axisymmetric dynamo, and that enabled him to do a nice two-scale analysis where you had the dominant part was axisymmetric, and then there were small components of non-axisymmetric fluctuations, and the ratio was essentially the magnetic Reynolds number. And then you could do a nice consistent expansion procedure, which enabled him to work out a fairly detailed model of what such a dynamo would look like. But his dynamo was non-axisymmetric. I mean, the non-axisymmetric parts were crucial, but they were small, but they were crucial. And they're then in the ratio of Rn.
You show the maps or the distribution of the magnetized rocks on the Martian surface, and then you also say that it should be a dipolar field, but this distribution looks not really that it was a dipolar. Maybe a hemispherical dynamo. Is it also possible for us?
Okay, I think that's a fair point. Actually, I mean, I said that Mars's field was dipolar. I mean, some of the models suggest that other people would disagree with that, and there isn't. I mean, because the field is the remnant field that's left behind is rather a mess. It's probably not really possible to say that. So,
okay. So it could be also a dynamo what just works on one hemisphere or something like that.
It could be. It could be.
Okay.
Can I ask a second question? Yes. It's about Saturn. You show the shells of Saturn, and the core was colder than the dynamo layer or the layer above. I was a bit surprised that it's colder in the middle. Was this third or fourth slide?
Right back near the beginning, was it?
Yeah, it was the fourth, I guess. Yes, the one in the middle. There's the rock and ice core is colder than the mixed layer. I mean, convection can also work if the buoyancy is in the other direction, but...
Yeah, no, that is a bit weird, actually.
Or is it
a bit weird? I must admit I haven't noticed that. I suspect that's a typo. No, I think that's almost certainly a mistake. Actually, no, sorry. I'll check that up. Well spotted. No, it's impossible. That's impossible. It's impossible. The temperature grade's always got to be that way. That's completely impossible. So, I hasten to say that was stolen from somebody else.
Okay, so we have some 15
minutes break or something, and then we have 2 seminars to conclude today. At this point, I could also remind you, in the Norida main building, there's also a second floor, which I forgot to show to my group, unfortunately. In the middle, once you come up the staircase, there's another biggish office with at least 8 desks. So that too would provide space for sitting, but otherwise, of course, the 2 lecture rooms and the coffee room, and there's wireless everywhere. And of course, here in this main building also. So there's certainly enough space to sit.